One day in Patimura University on a sunny morning.
Back with me, Nursari Suneth on Bad News. This time we will be delivered the author update in Poka by Mulia, our reporter and location.
Welcome to the weather forecast. Now, let's see what the weather is like today. As you can see right now in Poka, there is heavy rain with lightning for the next few hours.
By the way, there is a student who all alone watching a video with sweat in all of his face. Well, he's actually watching an education video from YouTube about transition state theory.
Marilah seluruh rakyat Indonesia arahkan pandangan ke depan. Raihlah mimpimu bagi nusa bangsa satukan.
Waduh, why this subject can be so hard to understand?
Bro, what's wrong with you?
The subject from our lecture about transition state was too hard for me to understand. Can you teach me about it?
That is very easy. Let me teach you about his theory. So, I think Wulan will explain into us.
The transition state theory, also known as absolute reaction rate theory, was first given by Marcelin and developed by Eyring and Polanyi. According to this theory, the reaction molecules are first transformed into intermediate transition state, also known as activate complex. The activate complex is formed by loose association or bonding of reactant molecule or by redistribution energy. The activate complex is unstable and breaks into the products at a defined rate as follow this picture. The activate complex has been considered a separate entity and there exists an equilibrium between reactant and activate complex. The concentration of activate complex can thus be obtained by applying the equilibrium condition. Energy of activation is additional energy which should be supplied to the reactant in order to form activate complex or to reach at the peak of the energy barrier. One vibrational of degree of freedom of the activate complex is quite unstable and responsible for disturbing activate complex into the products. The frequency of such vibration will be low and average will be the order of kBt. The rate at which the complex breaks up into the products. The rate of reaction depends on two factors. The factor one is concentration of the activate complex, and the factor two is frequency of vibration of the activate complex.
Yaps, the transition state theory was just like that.
Oh, now I understand.
And that is how we understand about the transition state theory. What a very sunny morning. Here is more explanation about the transition state theory by our friends SD and Riona.
Hello guys, now the article that we will explain is entitled Quantifying the Limits of Transition State Theory in Enzymatic Catalysis by Kirill Zinoviev and Inaki Tunon from Department the Química Física Universidad de Valencia, Spain, and edited by Donald G. Truller from University of Minnesota, Minneapolis, and approved October 3rd, 2017. While being one of the most popular reaction, the rate theories, the applicability of transition state theory to the study of enzymatic reaction has been often challenged. The complex dynamic nature of the protein environment raised the question about the validity of the non-reversing hypothesis, a cornerstone in this theory. Transition state theory is the most popular theory to calculate the rates of enzymatic reaction. However, in some cases, TST could fail due to the violation of the non-reversing hypothesis at the transition state. In the present work, we show that even for one of the most controversial enzymatic reaction, the hydride transfer catalyzed by the hydrofolate reductase, the error associated to TSD represents only a minor correction to the reaction rate. Moreover, this error is actually large for the reaction in solution than in the enzymatic active site. Based on this finding and on previous studies, we propose an enzymatic shielding hypothesis which encompasses various aspects of the catalytic process. The basic assumption in TST that there is hypersurface in this configurational space, the transition state, separating reactants and product bases that is never recrossed by trajectories coming from the reactant side. Then discussion about the validity of TST in enzymatic catalysis can be recast as a question about the validity of this non-reversing hypothesis and quantified by the transmission coefficient, the ratio between the true rate constant and that obtained from the application of TST, where transmission state is smaller or equal to unity. When transmission state is 1, there are no recrossing of the TS and the TST rate is exact. Non-recrossing assumption also implies that the distribution formed at the TS by the reactive flux in equilibrium 1. According to this, the rate constant can be evaluated from the free energy difference between the reactants and the TS. The transmission coefficient is not an intrinsic property of the system.
From the values of the transmission coefficients at the equicometer, we can conclude that the error due to recrossings of this hypersurface is actually smaller in the enzyme than in water. It's hard to find a physical interpretation for this fact, since it's not clear what features of the energy landscape are responsible for the appearance of recrossing pairs. The present analysis provides a numerical estimate of non-equilibrium effects, measured as the total TST error due to equicometer recrossings. The TS geometry has low sensitivity to the quality of the RCS tested. As a result, when one is interested only in the geometry of the TS, a simple coordinate, such as the transfer coordinate, can provide a reasonable result. This finding is in line with the tremendous success of free energy-based computational methods in enzymology.